Hello, Mr. Cash, and this is our Exoplanet project of the K2-172C by myself, Anthony Derzu, Mathis, and Emmerich. So let's start with the photon flux and the two transit durations. So photon flux over time gives us the chance to know the time that allows us to do a light curve, which will give us the properties of the star's planet system. TT is the total duration, which is the start of the decrease and the end of the rise of the brightness. TF is the full duration amount of time the planet is fully over the surface of the star. Now, for the stellar radius, mass, effective temperature, and radial velocity. If the depth of the exoplanet gets bigger, the nearer that the star's radius and mass, also named stellar mass and stellar radius. Effective temperature gives us the quantity of heat that the star will radiate per unit of surface area. Radial velocity now, this depends on the period, the stellar mass, orbital eccentricity, and orbital inclination. So you can see that the radial velocity depends on many factors. For the calculated parameters, so the planetary mass and the planetary radius is the mass and radius of our exoplanet. The density now is the degree of consistency that was measured by the amount of mass per unit volume. The volume now is the amount of space that an object or a substance occupied. So as you can see here, Mr. Cash, this is a table with all the results. So as you can see, you have the planet ID and all the calculations that we made and some data that we collected from NASA directly. I won't go through it in this presentation because it would take a lot of time and you could see it anyways on the Google Doc. So now let's pass to the possible composition of the K2-172C. So now for the possible composition of the K2-172C, we could compare it to our planet Earth in our solar system, since it's the closest planet to have a similar density to our planet. So like I told you, we need to look at the density, and the density of our exoplanet is 7.962 times 10 to the 12 kilogram per kilometer cube, and the density of the Earth is 5.51 times 10 to the 12 kilogram per kilometer cube. So it has a similar composition than planet Earth, since the values of both densities are kind of similar, they're close. And the Earth is composed in major part of oxygen and silicon, and we should expect to have the same composition on the K2-172C. Now let's pass to the seasons. So on our planet, with the calculations, we found that the gravitational acceleration of our planet is 2.23 meters per second square. Earth has a gravitational acceleration of 9.81 meters per second square. So we can say that on our planet, life is not likely to be suitable. The seasons are in most part determined by the actual tilt of a planet, and an ideal planet would be somewhere in between this range, like Earth, that has a actual tilt of 23.5 degrees. The actual tilt of our planet is undefined, so we will have to use other parameters to find out more about our planet's seasons. The orbital period can also tell us a lot about the distance of a planet to its star. A short orbital period would mean that the planet travels a shorter circumference around the star, so it has to be closer to it. The orbital period of our planet is really small, which is 29.6 days if we round it up. And that means it's a lot shorter than the Earth's period, which is 365.25 days. The mass of our planet star is 0.9 of the mass of our sun, if we round it up. And this means that the planet is a lot closer to a star that is basically the same mass as our sun. The seasons, unfortunately, are going to be extremely hot. So, like I told you earlier, that the planet is closer to its stars, so the seasons are going to be extremely hot, and most likely there won't be any liquid water on our planet. For the orbital eccentricity of the planet will also affect its seasons. A planet with a circular orbit around its star will receive a constant amount of light throughout its period, while a planet with an elliptical orbit will have varying amounts of light throughout its period, since its distance from its star will vary. A value of 0 for orbital eccentricity means a perfectly circular orbit, while a value of 1 means that the deviation from a perfectly circular orbit is at its maximum and the orbit will be highly elliptical. Our planet's eccentricity is at 0.999, so the orbit will definitely be elliptically shaped. This means that the season will drastically vary and it is not suited for life. A circular orbit would have been far better since it would have gave us more stable seasons. For our planet to be able to sustain life, it needs to be in the habitable zone range. For our planet, this range is in between 0.63 astronomic units and 1.5 astronomic units. Our planet's semi-major axis is at zero point 0.3 astronomic units, so it is much too close to its star and way too far from the habitable range. It is therefore cannot sustain life. Now for to finish the atmospheric composition of our planet. So the composition of the atmosphere of our exoplanet is undefined. The objective is to understand the temperature and composition of the atmosphere. When you are attempting to see an exoplanet that is far away, the starlight that will be going through its atmosphere will be able to be detected. Many elements can absorb the lights instead of allowing the light to go through. They can only absorb some part of the light spectrum, and this creates what's called a light signature, which is found by using a spectrometer, that is an instrument that can detect the light passing through the atmosphere. By having the light spectrum, that can be also called the visible spectrum, we can discover the different elements that are in the atmosphere. We can compare the atmospheric composition of our exoplanet to a planet like Earth that is in our solar system, since it would be made in major part of nitrogen and oxygen. Thank you, Mr. Cash, and I hope you have a nice day.